Hello, so I'm Aditya. I'm hosting this session today. Um and I'd like to welcome Ram and Naimish, who are going to talk about tropical cyclone trajectory modeling. And this topic is, I guess, a natural progression from the earlier two topics of viscous fluid flow, data analysis, and demand forecasting. Very similar statistical techniques might be used, I suppose. I'm excited to hear what they have to say. So take it away. While you're figuring out the screen sharing, I'll just add that I'm happy to have people in my own time zone also presenting. That's not very common in a remote conference, international conference. So thanks, guys.
Yeah, is the screen visible?
Yeah. All
Okay.
right. Hello, everyone. Good evening from India. My friend Naimish and I are honored to present a talk about modeling the trajectories of tropical cyclones using SINDy and satellite imagery. We'll be going through the purpose statement, some explanations and terms associated with tropical cyclones, what we did for constructing our dataset, some details about what SINDy is and how we're using it, system modeling, and finally the results of our experiment. Purpose statement. Naimish and I have been surviving cyclones for almost every year up to now in our lives. Both of us live in coastal metro cities, and cyclones are a yearly phenomenon. They wreak havoc, cause a lot of death and destruction wherever they make landfall. They also cause severe damage to property and infrastructure. The roads become flooded. There's no power for days. People living in ground floors have water enter into their homes. Um, we use satellite imagery and SINDy model to track satellite trajectories so that we can keep people informed and help them mitigate the damage that might be arising. Some questions. What are tropical cyclones? They are powerful rotating storms. They form over warm ocean waters near the equator. They bring strong winds, heavy rains, and high waves. They're also known as typhoons or hurricanes based on wherever you how are they currently being forecasted? A combination of computer models that simulate atmosphere, ocean, satellite data, along with some real-time observations from aircrafts and birds. These models analyze factors like wind patterns, sea surface temperatures, and atmospheric pressure to predict the trajectory of the cyclones. What is SINDy? Sparse identification of nonlinear dynamics, or SINDy, is a data-driven method that discovers the underlying mathematical equations governing a system's behavior directly from the measurement data. In this case, the data is the cyclone trajectory data. We took inspiration from these papers for this project. We've taken results from all of these papers to construct our SINDy model. Eventually, we'll be explaining which paper does what. So, moving forward, let's look at some of the important details and terms regarding tropical cyclones that are necessary to understand the details about the SINDy model. So we need to know how cyclones form, what their structure is, how they move, how do we forecast them, more importantly, why all of these questions are important to us. So without any further ado, let's get started. Just so that we're on the same page before we move ahead, depending on wherever you're from, you probably know these terms by a different name, but they're all governed by the same physical phenomenon. So cyclones form as warm, moist air over the ocean rises. While this happens, the air cools and condenses, releasing heat into the atmosphere. This heat warms the surrounding air, making it lighter and causing it to rise even further. The rising air creates an area of low pressure, which draws in more air from the surrounding environment, leading to a spiraling inward movement of wind. The Earth's rotation influences the direction of the swirling air, causing it to rotate counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. Existing atmospheric disturbances like easterly waves can provide the initial nudge for a cyclone to develop and intensify. Let's now understand what a cyclone looks like. Cyclones have four main parts to them: the eye wall, rain band, and outflow. The eye of the storm is a central clear sky area around which this cyclone rotates. The eye wall is a wall of clouds around the eye that has the highest sustained winds of the storm. The cyclone has spiral rain bands of thunderstorms extending outwards from the center, and the outflow is the high altitude winds flowing from the top of the storm that helps it maintain its strength. In order to understand how cyclones move the way they move, we need to first understand a few terms. The first one is steering winds, which are high altitude winds, usually found in the mid to upper troposphere, that play a key role in guiding the movement of large scale weather systems like tropical cyclones and low pressure areas. These winds don't cause the storms themselves, but they act like a conveyor belt, pushing them along. Forecasters closely monitor these winds because they help predict where a storm is likely to go. The second term is a Coriolis force. The Coriolis force is caused by the rotation of the Earth in space. As the Earth rotates, it exerts a slight force that causes moving air and water to deflect right in the northern hemisphere and left in the southern hemisphere. This force increases the further you travel from the equator. The trade winds are also caused due to the Coriolis effect. The final term we need to acquaint ourselves with is beta drift. Basically, beta drift refers to a natural westward and poleward motion that occurs even when steering winds are weak or absent. This drift happens because of the variation in the Coriolis force with latitude. As the storm circulates, it interacts with this gradient, producing a slight northwestward shift in the northern hemisphere. Putting everything together, cyclones move primarily due to large-scale steering winds in the atmosphere. The Coriolis force causes cyclones to rotate and influences their direction, pushing them poleward and curving their path. Beta drift causes a slow northwestward motion in the northern hemisphere due to variation in the Coriolis force with latitude. Interaction with high and low pressure systems can alter their track. Land interaction and changes in ocean temperature can slow or change their path. Vertical wind shear, which is the changes in wind speed or direction with height, can weaken or steer cyclones. Here's a plot of cyclones and their distribution globally since 1851. You may be wondering why South America seems not to have any cyclones there. Well, the reasons are pretty straightforward. South America is shielded by cool waters, strong winds aloft, the equator's low spin, and mountains, making tropical cyclones extremely rare on both coasts. Both coasts of South America typically have sea surface temperatures too cool to support cyclone formation, and much of South America's northern coastline lies too close to the equator for the Coriolis force to be strong enough to produce cyclones. And here's a map of the global ocean currents for your reference. Now that we know how cyclones form, let's look at how they're currently being forecasted. The image on the right is a bulletin from the Indian Meteorological Department for Cyclone Rimal over Bay of Bengal in 2024. We see the forecasted track in red and the observed track in black. The forecast is generated by a mix of satellite imagery, radar data, aircraft reconnaissance, and numeric simulations. Why does cyclone trajectory forecasting matter? Because it saves lives, protects communities, and reduces economic losses. Accurate forecasts give people time to evacuate, secure homes, and prepare emergency supplies before the storm hits. Governments and disaster response team can position resources and plan evacuations more effectively. In regions where infrastructure is vulnerable, early warnings can mean the difference between manageable disaster and a humanitarian crisis. With climate change making storms more intense and unpredictable, reliable cyclone forecasting is becoming even more critical for building resilient societies. A significant number of modern features in cyclone alerting systems can be traced back to Cyclone Bhola. In 1970, Cyclone Bhola struck East Pakistan, now Bangladesh, becoming one of the deadliest natural disasters in history. Over 300,000 people lost their lives, mainly due to the storm surge and lack of early warning systems. Early warning system had changed from a scale of 10 to a scale of 4, causing locals not to take the Cat 4 warning seriously. Satellite imagery for the cyclone was available before landfall, but it was only processed 7 days after the cyclone hit. The cyclone had 20 feet storm surges and hit land that was barely 5 feet above sea level, causing island-wide depopulation. The disaster exposed several government neglect and inequalities, fueling public anger and unrest. This led to mass political protests and ultimately played a role in the birth of Bangladesh in 1971. The geopolitical fallout from this cyclone almost caused a nuclear war. If anyone wants to learn more about it, I'd strongly recommend checking the book, The Vortex Out. It's a fascinating read. I'll let my friend Naimish take over now and talk to you about how we constructed our dataset.
Thank you, Ram. I hope I'm audible. And
Yeah.
yeah, good. Yeah. So let's get started with how we got our data, where we got it from, and what we're doing with it. Right. So we get our data set from two main sources, the IBTrax dataset and the MVIRI dataset. The IBTrax dataset is a World Meteorological Organization collaborated dataset of all cyclone tracks across the world at a 3-hour time resolution, and it goes as early back as 1973. We have earlier records as well, but they're not as comprehensive as the ones from 1973. The MVIRI, which is the Meteosat Visible and Infrared Imager dataset, is a geostationary satellite image dataset shot by the Meteosat 7 satellite, which was launched by EUMETSAT, the European Union's meteorological satellite agency, as a part of their Indian Ocean data campaign. The satellite was parked at 57 degrees east longitude. The satellite images are available at a 30-minute time resolution. So, in order to build any model, we first need to know what we need and what data we have at hand. From the presentation so far, I hope it's clear that we need the cyclone's current position, the wind velocity, wind shear, and beta drift values in order to build any future position forecasting system. We get the cyclone's position from the IBTrax dataset, and we can calculate the wind velocity and shear from satellite imagery. And we pray our model accounts for the beta drift. Let's see how we proceed with that. Right. So first, we'll look at the IBTrax dataset. This is a plot of all the cyclone tracks from the IBTrax dataset between 2007 and 2016. We can see that we have many more cyclones on the right half, which is the Bay of Bengal, than the left half, which is the Arabian Sea. This is because the Bay of Bengal tends to be warmer year-round, especially during the cyclone season. The bay receives vast amounts of fresh water from the large rivers, the Ganges and the Brahmaputra, which increases the which reduces the salinity of the ocean, which makes it easier for heat to build up and fuel cyclone formation. Similarly, the Western Ghats, the hills along the western coast of India, also prevent these moisture heavy winds from moving from the Bay of Bengal to the Arabian Sea, which further reduces the possibility of cyclones forming over the Arabian Sea. Although this has been changing in recent years due to global warming. So, the satellite. The satellite we're getting our data from is the Meteosat 7 satellite. It was launched in 1997 by the European Space Agency for monitoring above the Atlantic Ocean. In 2006, it was repositioned over the Indian Ocean to take over after the satellite over the Indian Ocean failed. It finally retired in 2017 after nearly 20 years of service. Unlike regular color cameras, the imager on the Meteosat 7 satellite works slightly differently. Your normal cell phone camera, for example, combines the red, green, and blue light to produce full color images. The satellite's imager does not work with visible color in that way. Instead, each imaging channel captures intensity values, which is how much radiation is being detected in that specific band, and it results in a grayscale image. A bright spot in the infrared channel might mean high, cold, like dark clouds, and a dark area in the visible channel might mean land with less reflected sunlight. So this is what the satellite images look like. The individual channel images look like from the Meteosat 7 imager. We have the infrared band on the top left, the visible on the top right, the water vapor on the bottom left, and a false colored composite on the bottom right. We primarily work with the infrared and water vapor channels in this project because the visible channel's output changes significantly with the time of day. The position of the sun, as we can see here, influences the light that is being reflected back from the earth. Whereas when it comes to infrared and the water vapor wavelengths, they are not directly related to the amount of solar radiation that is falling at any given time. So we can get them all day round. So the next slight detour we need to make before we can get into the data processing is optical flow. In computer vision, we have an algorithm called optical flow. This algorithm compares subsequent video frames to identify how the pixels are shifting between them. This in turn is used to calculate motion vectors that help us identify how objects are moving across the scene. As you can see in this case over here, the motion vectors show how the directions in which each vehicle is moving on the road. We use this technique to calculate the motion vectors of clouds in our satellite imagery. So finally, we have all of the building blocks required to produce our dataset from the satellite imagery. Here's a quick rundown of the steps. First, we downloaded the raw images from EUMETSAT and we processed them to get the wind velocity vectors through optical flow. We calculated them separately at the water vapor and infrared wavelengths. Then we took 1 degree geodesic bands around the center of each cyclone and we averaged the velocity in each band. Then we further resolved these velocities into their x and y components and produced our final dataset of 1190 rows for 26 cyclones between 2007 and 2016. The banding was done in order to reduce the dimensionality of the image dataset to make it easier to train our machine learning models downstream. Cool. So now that that's out of the way, let's look at SINDy. Ram Narayan mentioned SINDy at the starting of the presentation, and now we'll finally understand how this works. We just need to get a feel for it though, because it is slightly maths heavy and there is a lot of Greek and Latin every now and then. If it sounds like Greek and Latin, that's because it is Greek and Latin. So it's fine if we don't fully get it on the first go, right? Cool. So what is SINDy? SINDy is a data-driven technique that discovers the underlying mathematical equations governing a system's behavior directly from measured data. It analyzes time series data to find simple, interpretable equations that describe how a system changes over time. It works by using sparse regression to identify the key terms that best explain the system's dynamics. We also use it to reduce complex high-dimensional data into concise models that can be used to identify physics from the system, or like also control theory as well, right? Let's first look at how SINDy works through a case study. The Lorentz system, which I'm sure some of you might be acquainted with from previous sessions, is a very classic example that is used to explain and understand how SINDy works. The Lorentz system is a chaotic dynamical system developed by Lorentz in 1963. The system is governed by three ordinary differential equations involving the variables x, y, and z. Despite the simplicity of the equations that we'll be looking at soon, the Lorentz system exhibits highly complex chaotic behavior sensitive to initial conditions. On the right, we have a plot of the Lorentz attractor in 3 dimensions. Let's see how this plot was made. So we have the differential equations on the left, and we have the integrated observation data on the right. We'll be using the observation data on the right to build a SINDy model down the line. So the equations on the left, and then we can see the graph on the right over here. Cool. So through integration, we get our observation data. The next step from the observation data involves constructing a candidate matrix of all possible linear and non-linear combinations of the observable data. For example, we have the second, third, and fourth columns, that is x, y, and z, directly from our observation data. Then we add a constant column, and then we have x square, xy, y square, etc., etc. We can also take trigonometric functions, exponential functions, logarithms, and any other combinations that we want in order to construct this extremely large candidate search space. Whatever terms we feel might be present in the differential equation that might describe the system of our observation data is added to this candidate library. Then we get to Lasso regression. As Anton mentioned during the previous talk of ridge regression, Lasso regression is an L1 regularization term. The maths, it's fine. We don't need to get into it too much. But basically what Lasso regression does is it drives the less important coefficients to exactly 0, which makes it easier to reduce the dimensionality of our dataset. And hence we get rid of a lot of terms that might not necessarily be impacting the governing equations of our system. Since many of these candidate functions are likely irrelevant to our true systems dynamics, as from this extremely large candidate table we've constructed, Lasso regression provides a very significant role in the SINDy system. Cool. A footnote on Lasso regression before we continue. Models that generalize well are more useful in practice than models that fit well. In real world applications, the goal isn't to just fit the training data perfectly, but it's to make accurate prediction on new unseen data. Overfitting happens when a model learns not only the underlying patterns, but also the noise in the training data, which might hurt performance on future data. Lasso helps combat this by simplifying the model. It keeps only the relevant features and sets the rest to 0. This leads to models that are easy to interpret, faster to compute, and more robust to noise. This is especially useful when it comes to building a physics-informed system such as this, because our candidate library has a lot of terms, and most of them are most likely irrelevant to the final system at hand. So we train the Lasso model to predict dx, dy, and dz. From that, we can get the coefficients as described in the table above. And we can see when compared to the expected coefficients in the table below, the Lasso regression model does tend to do a pretty good job at predicting the coefficients for our Lorentz system. Finally, we just read out the coefficients that produce a differential equation for our system. We can see that the SINDy equation does have a few more terms in the original equation, but it isn't too far off. And then finally, we can integrate the equation, the differential equation produced by SINDy to get our forecasted trajectory. So just to recap, we're looking at the slide again, but I hope now we have a little better understanding for the different building blocks in the slide. We take our state observations, we construct our candidate matrix, we run Lasso, estimate our coefficients, and then finally integrate them to produce our observation data. Cool. Now let's finally get to the cyclone modeling, which is what we're here for. We have all the building blocks. Now we get into the maths. So what did we need? We needed position, velocity, and beta drift. We have IB tracks, satellite imagery, and we are hoping our model can account for beta drift when we train it. Now, because there is a lot of pre-existing literature on how cyclones form and how they move, we can incorporate some of the known physics into fine-tuning our candidate library instead of constructing an extremely large sample search space. From one of the papers we went through, we got the following relations between the position, velocity, and shear from the environmental flow. Similarly, we have another relation between wind velocity at different altitudes and beta drift. By combining both of these differential equations, by combining both of these relations together, we get this final form of a very large differential equation that we then use to construct our candidate library. As you can see, we have a f of term, a g of term, and an h of term. And we build our candidate library to account for these terms as well, especially account for these terms. Right. Now let's look at our results. So performance matrix. There is an asterisk next to SINDy. I will get into the explanation behind that when we get to the discussion section, but let's just look at this for now. Right. SINDy 43.71 kilometers. We compared it to other standard regression techniques. OLS, gradient reboost, random forest, and like just normal lasso regression. You may be wondering why SINDy performs worse than all of them. We'll get to it in a while. But what Anton mentioned during his talk will also feature in our results discussion. So that is something to look forward to, I hope. Cool. So let's look at the SINDy's predicted track. The ground truth track is in red, the forecasted track is in green, and then we have the random forest prediction, we have gradient reboost prediction. So discussion. In tropical cyclone track forecasting, getting a position estimate of under 50 kilometers is considered to be a good result. The traditional regression models were not doing auto-regression. They were only predicting the exact next time step. Whereas with SINDy, we were predicting the entire trajectory from different seed points. Hence, although both of them do have the mean absolute error as a common error metric, it is not an apples to apples comparison. Auto-regression, especially when we try to apply it for these kinds of cases, deteriorates very quickly, and the errors you get from it are astronomical. We ran it. I think we got more than like 400 kilometers of errors in that. So we just decided not to do auto-regression with the normal machine learning other models. Also, the Bay of Bengal cyclones experience stronger land effects when they come closer to land, causing them to curve east than the Arabian Sea cyclones. The Arabian Sea cyclones just tend to move to the west. This might explain the overall poorer performance of SINDy against other models as well. Similarly, a larger candidate library could also be constructed with more nonlinear terms in order to see if we can find a better, more robust model. So here's a look at the libraries we used for this. We used Clay and Nudge, obviously. We also used Tablecloth, Metamorph, and Smile for our models. So thank you so much for your time. I hope we didn't ramble too much about this, and I hope you managed to at least understand some of the stuff we were talking about. And please feel free to ask us any questions you may have regarding this.